Hi guys, my name is Ayman Umal and I'm gonna be reporting about fundamentals of traffic flow. Under it are flow density relationship and shock waves and traffic streams. So let's proceed. Traffic flow is the study of interactions between travelers, including pedestrians, cyclists, drivers, and their vehicles, and infrastructure, including highways, signage, and traffic control devices, with the aim of understanding and developing an optimal transport network with efficient movement of traffic and minimal traffic congestion. So, next is the types of traffic flow. There are two types of traffic flow, and the first one is uninterrupted flow occurring at long sections of road where vehicles are not required to stop by any cause external to the traffic stream. So, uh, a good example of uninterrupted flow is can be located at national highways, like outside city properties, or located at good example is the Pan Philippine Highway, National Highway. And the second one is interrupted flow occurring at long sections of road where vehicles are required to stop by any cause outside the traffic stream, such as traffic signs, and traffic signal lights. So a good example of this can be seen at city properties and metropolitan areas. So next is primary variables of traffic flow. So as you can see, these variables are discussed by a previous reporter, and under the primary variables of traffic flow are the first one is flow rate or volume, which is the Q. Next is speed, can be uh, substituted as U or V. And this one is density or concentration, which is K. And the other traffic flow variables are time headway, which is H, spacing of the vehicles, S, and time occupancy, which is O. Next is flow density relationship. Based on the definitions presented by a previous reporter, as we have as the previous reporter discussed, a relationship exists among the three primary variables, which are traffic flow, speed, which is the space mean speed, and density, denoting space mean speed as simply U for notational convenience, where Q is equals to U sub, sub S K. So Q, which is the flow rate, is equals to space mean speed times density. So next is, here are the key equations we need to remember when dealing with problems regarding flow density relationship. So Q is equals to K times U, which is flow times density times speed, which is flow is the unit of flow is vehicle over R, and H, which is the headway, 1 over Q, which has a unit of seconds per vehicle, and converted to R, which can be R per vehicle, and S is equals to 1 over K, which is S is the spacing of vehicles, can be denoted as feet over vehicle, or can be converted to miles per vehicle. So next is flow density relationship. So here are the diagram of flow density relationship. Also mean speed density relationship and mean speed and flow relationship. So here is the other curve diagrams. Traffic flow curves, maximum flow, jam concentration, free flow speed. So here on the upper left corner, which is the speed density relationship, lower left corner is the flow density relationship, and the upper right corner is the speed flow relationship. So as you can see here, Q max is regard means that it has a maximum flow. So here in the flow density relationship, Q max is located at the mean density. So it is so Kj, which is the can be located at the end point of K, which is regarded as jam concentration, or the maximum vehicles located in the along a line. So u the speed is u, and if the speed is u, or if the speed is 0, then K is maximum. Then uf, or the u sub f, or the free flow speed, K is the density is 0, and the speed is equals to free flow speed. Next is the slope. We're gonna be talking about the slope of flow density relation curve. Flow density curve. So the slope of the line connecting any point on the curve and the origin is the space mean speed. So here we can see that the maximum flow, or the capacity, occurs when the speed of traffic stream is half of the free flow speed. So the maximum flow, which is the volume, occurs when the speed of traffic stream is half the free flow. So half of the density, if the density of the vehicles is located in half, then the free flow, or the volume of the vehicles, is in maximum. Next is the maximum flow, or the capacity, occurs when the density is half of the jam density. So the it is also the same. The maximum flow can be located when the speed is half and the density is half. Therefore, the maximum flow, or the Q max, is equals to half of speed over half of density. So Vf over Kj over 4. That is the general equation we're gonna be using when dealing with flow density curve. So here's the other formula when using the when dealing with flow density curve. Here is Q is equals to U speed, free flow speed, times density minus density squared over jam density. So here Km is located at the midway, and the jam density is located at the end point. So maximum flow, or maximum volume of vehicles, can be seen at the optimal density of the curve. So on the right side is the congested flow, and the left side is the uncongested flow. So basically, this means that if you have more density, it means that it is actually packed or jammed. And when less density is equals to uncongested flow. So next is general properties for any traffic flow model. Need to satisfy 4 boundary conditions. First is flow is 0 at 0 density. So at 0 density, the flow must be 0. So it should be proven that the flow, or the volume of the vehicles, are at a, are at a stop when the density is 0. So next is flow is 0 at maximum density. So as we have tackled here, if the flow is if the density is maximum, so the flow is 0, and also when density is 0, so the flow is also 0. So it is true on both statements. Next is mean free flow speed occurs at 0 density. Next, flow density curves are convex, so there is a point of max flow. So here we can see that the flow density curve is a convex type, so we can see that there is a maximum point we can locate. So next is fundamental diagram of traffic flow, which is the flow density under the flow density relationship. First one is almost zero density, free flow speed, very low volume. So next is increased density, reduced speed, increased volume. So when increasing density, the speed is reducing and the volume is also increasing. So more vehicle, less speed, more vehicles. Increased density, reduced speed, max volume. So increased volume of vehicles, maximum volume vehicles, so uh, minimum speed. So it's gonna be pack jam density. So next is jam density, minimum speed or crawling of vehicles means very low volume. And the next one is examples. So here, data obtained from aerial photography showed 6 vehicles on a 600 feet long section of road. Traffic data collected at the same time indicated an average time headway of 4 seconds. Determine the density of the highway, the flow on the road, and the space mean speed. So given, which is the headway, which is the 4 seconds, the length 600 feet, and the number of vehicles, which is 6. So first, the density on the highway, which is the formula K is equals to number of vehicles over length. So 6 over 600, 0.01 vehicles per feet. So make converting it to miles, so times 5,280, so 52.8 vehicles per minute. So next is the flows or the Q. So Q is equals to 1 over H, or 1 over the headway. So 1 over 4 is equals to 0.25 vehicles per second. So converting it to hours, so the flow should have 900 vehicles per hour. So lastly, the space mean speed or the speed is equals to flow over density. So the answered question on letter B, which is the flow over the density. So 900 over 52.8. So the answer should have 17 miles per hour. Next is shock waves and traffic streams. Shock waves that occur in traffic flow are very similar to the waves produced by dropping stones in water. A shock wave propagates along a line of vehicles in response to changing conditions at the front of the line. Shock waves can be generated by collisions, sudden increases in speed caused by entering free flow conditions, or by number of other means. Basically, a shock wave exists whenever the traffic conditions change. So, shock wave is simply the motion or propagation of a change in density or flow. So whenever we are in outside traveling or using a transportation, you can always experience shock waves, like accidents or incidents like flat tires, uh, damaged batteries, responsible drivers, and etc. So next is here shock waves. Further explanation on shock waves. So here on the left side, we can see that S is the shock wave, the vertical line separating region A and B. So U sub W is the speed of shock wave. Positive if line S moves towards the positive X direction, so on the right side. So U sub 1 and U sub 2 space mean speeds in regions A and B respectively. So U sub R1 speed of vehicles in region A and the left side relating to the moving line S. So U sub R1 is equals to U sub 1 is equals to I minus U sub W. Same here on U sub R2, speed of vehicles in region B relative to the moving line S. So U sub R2 is equals to U sub 2 minus U sub W. So let N be the number of vehicles crossing at line S at time T. So equating both equating U sub R1 and U sub R2 times time. So substituting the value, we can produce the general equation for the speed of shock wave, which is the U sub W here on the right side, which is the U sub W is equals to Q2 minus Q1 over K2 minus K1, which is the flow over the change in flow over change in density. So here in the lower right side is the general equation can be represented in the flow density curve here. So here is slope U sub W, and the vertical component is the flow, and the horizontal component is the density. So next is example of shock waves problem. So here is the length of Q due to a speed reduction. So the volume at a section of a two-lane highway is 1,500 vehicle per hour in each direction, and the density is about 25 vehicles per mile. Then a large dump truck from an adjacent construction site joins the traffic stream and travels at a speed of 10 miles per hour for a length of 2.5 miles. Vehicles just behind the truck have to travel at the speed of the truck, which results in the formation of a platoon having a density of 100 vehicles per mile and a flow of 1,000 vehicles per hour. So the question is, determine how many vehicles will be in the platoon by the time the truck leaves the highway. So solution is using the general equation of shock waves, general equation for the speed of the shock waves. So change in flow over change in density. So Q2 minus Q1 over K2 over K1, K2 minus K1. So Q1, which is the flow 1, is the 1500 vehicle per hour. K1 is the 25 vehicles per mile, and Q2 is the 1000 vehicles per hour, and K2 is the 100 vehicles per mile. So step 1, finding the speed of the shock wave. So substituting all the given items, so which results in negative 6.7 miles per hour. So the speed of the shock wave is negative 6.7 miles per hour. So the growth rate of platoon, next step 2 is 10 miles per hour, which is at the second statement, plus the computed speed of shock wave will equate to 16.7 miles per hour. So the time the truck will leave the highway, so distance over the speed. So 2.5 miles over 10, so 0.25 hours. So the length of platoon, so is will equate to time times the uh, growth rate platoon. So 0.25 times 16.7 will equate to will result to 4.2 miles. So step 5, lastly, the Q length is equals to density times distance. So the density is equals to 100 times the distance of 4.2. So will result to 422 vehicles located in the along the highway. So that's all, guys. Thank you for listening, and if you have any questions, please comment or ask me directly. So thank you.